for variance. In this test, we assume that investigated feature has normal distribution. We consider two cases depending on the number of elements in the sample. In the case of the sample with not bigger than 30 elements, we verify hypothesis sigma squared equals sigma 0 squared against hypothesis sigma squared is not equal to sigma 0 squared, or sigma squared is greater than sigma 0 squared, or sigma squared is less than sigma 0 squared. And then we're using statistics at chi-squared equal ns squared divided by sigma 0 squared, or n minus 1 times s hat squared by sigma 0 squared, where s hat squared is variance and biased variance of the sample. This is the one divided by n minus 1. For these statistics, the critical regions also depend on the form of the alternative hypothesis, and we have the following critical regions. For sigma squared different from sigma 0 squared, we have two intervals from 0 to chi-squared of alpha 1 union chi-squared alpha 2 squared to infinity. In case of the second case, we have chi-squared alpha infinity, and in the third case we have from 0 to chi-squared alpha. The funny thing is that chi-squared is never negative. That's why the critical regions always start at least from 0. Now we have a picture where it is all shown. Critical regions for chi-squared tests. Okay, so in the middle we have the two-tailed test. On the top we have the upper one-tailed test, and in the bottom we have the lower one-tailed test. And here you have the cumulative distribution table for chi-squared. We can use it. In the column you can see different degrees of freedom, and alpha values you have for upper and lower limit, alpha 1 and alpha 2. On the left, the test of uniformity. So supposing we wanted to check that the data that we have obtained in observations are uniform with a certain fixed discrete probability distribution. So assume the probability distribution has only values x1 to xk, and all of them are assumed at the level of probability P1 pk. We want to test the zero hypothesis. P1 equals P01, P2 equals P02, and so on and so on, with given fixed P01, P0k, and we want to check if this distribution is uniform, or means the same, identical, equal to the distribution we have obtained. A random number generator that simulates 4 different values was tested. It was decided to check if each value appears with the same probability. For this purpose, based on observations, The following table has been prepared. We can see we obtained the number of observations was, for the first value was 96, for the second 95, for the third 110, and for the fourth 99. It seems that third value appeared a little more frequently, and the first two values more rarely, but is it by chance? We will test it. So verifying the truth of the sentence that each value generated appears with the same probability corresponds to testing null hypothesis of the form P1 equals 1/4, P2 equals 1/4, P3 equals 1/4, and P4 equals 1/4. Against the hypothesis alternative that P1 is not equal to 1/4, or P2 is not equal to 1/4, or P3 is not equal to 1/4, or P4 is not equal to it. Since n is very big, n equals 400, we have a sufficiently large number of observations. Therefore, we can use the chi-square compliance test. We have generated value number of times. It is good to find the expected value of the times of generations when assuming that all the probabilities are 1/4. So if all the probabilities are 1/4, we should expect 100 for each value, more or less. Okay, now we have to find the chi-squared. So it is equal to 96 minus 100. So we subtract the number of observations minus the expected number of observations squared divided by 100, the expected value. And the same for the next, 95 minus 100 squared over 100. And until the fourth. And we obtain the value of 1.42. What is the critical value in this test? First of all, it's a chi-squared test. It has two parameters. It has both the alpha value and the number of degrees of freedom. It's similar to t-student. Okay, so we know alpha. What is the number of degrees of freedom in this case? The number of degrees of freedom is 3. Because all the values can change, but anyway, the sum must be 1, so this is the simplest explanation. We have to shift to the table. Okay, as we can see, for the alpha equals 0.05 and 3 degrees of freedom, we obtain 781. But also we conclude that the sum of squares we obtained is less than the quantile for 0.95 and 3 degrees of freedom, and therefore we have landed in the acceptance region. So the conclusion is that there is no enough evidence to reject H0.